Okay, so in this section, we're going to talk about diagonalization of symmetric matrices, and this is one of the most important sections in linear algebra, and that is because there are a lot of application to this. So let us see the definition of symmetric matrix. So a symmetric matrix is a matrix such that A is the same as its transpose matrix. So for example, 1, 0, 0, and -3 is a symmetric matrix. And also 0, -1, 0, -1, 5, and 8, 0, 8, and -9 is also a symmetric matrix. And A, B, C, B, D, E, and C, E, F is a symmetric matrix. So do you see the pattern here? So basically, we call this as a symmetric matrix because, well, the entries are symmetric along the diagonal entries. And if you already had calculus 3, then if f of x comma y is a differentiable function, like twice differentiable function, then we can build a matrix such that like f sub xx, f sub xy, f sub yx, f sub yy as the partial derivative with respect to each variables, then this is also an example of a symmetric matrix because f sub xy is the same as f sub yx. And we call this as Hessian matrix. So let's see what are the group properties of the symmetric matrices. So suppose that A is given by this matrix and you want to see that A is symmetric along its diagonal entries. So compare all these entries. And suppose also that you have eigenvalues 8, 6, and 3 and corresponding eigenvectors -1, 1, 0, -1, -1, and 2, and 1, 1, 1. So let us see what happens when you take the product of vectors in different eigenspaces. So first of all, if you take the dot product with -1, 1, 0 and -1, -1, and 2, then this gives you -1 squared plus -1 plus 0, that equals to 1 minus 1 plus 0, which is just 0. And second, well, if you take the dot product with -1, -1, and 2, and 1, 1, 1, then this gives you -1 minus 1 plus 2, which again gives you 0. And lastly, if you take the dot product with -1, 1, 0, and the last one, 1, 1, 1, then this gives you -1 plus 1 plus 0, that equals 0. So this tells us that if you take vectors from different eigenspaces, like if you say this vector equals to v1, and this one equals to v2, and this one to be v3, then v1 and v2 and v3 form an orthogonal set. So using that, if you normalize each vectors, then we get an orthonormal basis. So if you say u1 equals to v1 divided by its magnitude, then, well, the magnitude of v1 equals to 1 over square root of like -1 squared plus 1 squared times -1, 1, 0. And this equals to 1 over square root of 2, -1, 1, and 0. And u2 equals to, so if you normalize v2, then this gives you, I guess the magnitude of v2 equals to 1 over square root of -1 squared plus -1 squared plus 2 squared times -1, -1, and 2. And this equals to, I guess, 1 over square root of 6, -1, -1, and 2. And u3, well, if you normalize the last vector, then we have like, so the magnitude of v3 equals to 1 over, so square root of, I guess, 3 times 1, 1, 1. Then we can tell that, well, if you say b equals to these three vectors, u1, u2, and u3, So negative 1 over square root of 2, 1 over square root of 2 and 0, and negative 1 over square root of 6, negative 1 over square root of 6, and 2 over square root of 6, 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3, then this is an orthonormal basis for R3. So now we can diagonalize A using the orthonormal basis of eigenvectors found in the previous part. So what it means is, well, we can tell P equals to U1 and U2 and U3, and this equals to I guess 1 over square root of 2, 1 over square root of 2 and 0, and negative 1 over square root of 6, negative 1 over square root of 6, and 2 over square root of 6, and 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. Then we have D equals to, so remember that we have to match each columns with corresponding eigenvalues. So it should be 8, 6, and 3, and the rest are 0. Then because P is an orthogonal matrix, or in other words, the columns of P form an orthonormal basis, we have P times P transpose equals to the identity matrix. So in other words, we can tell P transpose is the same as P inverse. So P inverse is given by simply transposing the given matrix P. So this equals to 1 over square root of 2, 1 over square root of 2, 0, and negative 1 over square root of 6, negative 1 over square root of 6, 2 over square root of 6, 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. And then we have A equals to P d P inverse, or in other words, P times D times P transpose. So that is not a coincidence for symmetric matrix. So if A is symmetric matrix, then any two eigenvectors from different eigenspaces are orthogonal, or in other words, they are perpendicular to each other. So let us see the reason why. So let's say V1 and V2 be eigenvectors with corresponding eigenvalues lambda 1 and lambda 2, where lambda 1 and lambda 2 are not the same thing. Then lambda 1 times V1 dot product with V2. Well, if you write this as a matrix product, then this equals to lambda 1 V1 transpose times V2. Or because V1 is an eigenvector, we have a V1 transpose times V2. And if you distribute the transpose into the parentheses, then this gives you V1 transpose times A transpose times V2. But we have A as a symmetric matrix, so this equals to V1 transpose times A V2. And if you look at in this part, then this gives you V1 transpose times lambda 2 V2. Or in other words, this equals to lambda 2 V1 transpose V2, or this equals to lambda 2 V1 dotted with V2. So this tells you lambda 1 times V1 dot V2 is the same as lambda 2 times V1 dot V2. So we have lambda 1 on V1 dot V2 equals to lambda 2 V1 dot V2. Or this is equivalent to half. So if you move things to the left hand side, then this gives you, well, lambda 1 minus lambda 2 times V1 dot V2, and this equals to 0. But we have that lambda 1 is not equal to lambda 2 because we picked vectors from distinct eigenspaces. Or in other words, this quantity never equals to 0. So that means V1 dotted with V2 is actually equals to 0. Or in other words, V1 is orthogonal to V2. Now, we call an n by n matrix A is orthogonally diagonalizable if there is an orthogonal matrix P. So remember that orthogonal matrix has a property that P transpose is identity, or if P is a square matrix, we have P inverse the same as P transpose. And here, if we can diagonalize the given matrix using orthogonal matrix P and the diagonal matrix D, then we say A is orthogonally diagonalizable. So if you apply this over here, then this gives you A equals to P dP inverse. So orthogonally diagonalizable matrix has an interesting property. So let's say A is orthogonally diagonalizable. Then we have A equals to P dP transpose. And if you take the transpose for the both sides, then we have this equation, and this equals to, well, if you distribute the transpose operator, then we get P transpose to the transpose times D transpose times P transpose. But if you take the transpose for 2 times, then that will restore your original matrix P, and D is a diagonal matrix, which is symmetric. And we have P transpose, but this actually equals to A. So if A is orthogonally diagonalizable, then we have A transpose equals to A. So if you combine with this observation with the theorem above, the theorem 2, then you can tell that, well, an n by n matrix A is orthogonally diagonalizable if and only if A is a symmetric matrix. And we call the set of eigenvalues of the matrix A as the spectrum of the given matrix. And this is one of the most important theorem in this section. So if A is a symmetric matrix, then A is orthogonally diagonalizable, or in other words, it is diagonalizable. So A has n number of real eigenvalues, counting with multiplicities. And this means that, like, if you have the characteristic polynomial equals to, say, like lambda minus 2 squared, lambda minus 1, then we're regarding that the matrix has eigenvalues like lambda equals to 2 and 1, counting with multiplicities. And because A is diagonalizable, the dimension of eigenspace for each eigenvalue equals the algebraic multiplicity of lambda as a root of the characteristic equation. And the eigenspaces are orthogonal. And this means that if you take eigenvectors corresponding to different eigenvalues, then they should be orthogonal each other. And lastly, the symmetric matrix is orthogonally diagonalizable. So let us check and verify whether we can orthogonally diagonalize the given matrix A with its characteristic equation 0 equals to negative lambda minus 7 squared plus lambda plus 2. So the first thing you want to check is whether A is a symmetric matrix. So if you see the matrix over here, then you can tell that, well, we have the symmetry along the diagonal entries. So the given matrix is symmetric. And the next step should be, so we have to find eigenvalues and the corresponding eigenvectors. So we have characteristic equation equals to this. So this gives you lambda equals to 7 or negative 2. But 7 is multiplicity 2 in this case, so you can expect there should be 2 different eigenvectors. So let us begin with easier case. So when lambda equals to negative 2, then A minus negative 2i, which is A plus 2i, equals to, so if you add 2i to this matrix above, then we get 5, negative 2, 4, negative 2, 8, 2, 4, 2, and 5. And if you take RREF of this matrix, then you will get 101, 0, 1, and 1 over 2, and 0, and 0, and 0. So this tells you that x1 equals to negative x3, and x2 equals to negative 1 over 2 x3. Or the solution set for the homogeneous equation, like a plus 2i x equal to 0, is we have negative x3, negative 1 over 2 x3, and x3. Or in other words, we get eigenvector negative 1, negative 1 over 2, and 1. On the other hand, when lambda equals to 7, then we have to calculate the null space of a minus 7i, and this equals to negative 4, negative 2, 4, negative 2, negative 1, and 2, 4, 2, and negative 4. And if you take REF of this matrix, then we get, well, I guess all the rows are linearly dependent. So it should be 2, 1, and negative 2, 0, 0, 0, 0, 0, and 0. So this gives you x1 equals to negative 1 over 2 x2 plus x3. Or in other words, we get the general element for the null space equals to negative 1 over 2 x2 plus x3 and x2 and x3. And this equals to, well, if you separate the variable, we get x2 times negative 1 over 2, 1, and 0, plus x3 times 101. So here we have two different linearly independent vectors, but they may not be orthogonal each other. So we have to force them to be orthogonal. So how do we do that? We should apply the Gram-Schmidt process to get orthogonal basis for the given eigenspace E sub 7. So this should be step 1/1 or 1-1. So if you let this vector equals to v1 and that one equals to v2, then the Gram-Schmidt process tells you that, well, if you set the z2 equals to v2 minus the projection of v2 onto v1, which is v2 dotted with v1 over v1 dot v1 times v1, then this new vector z2 is orthogonal to v sub 1. So this gives you, we have negative 1 over 2, 1, and 0, minus, so if you take the dot product, we get negative 1 over 2 over 1 plus 1, and multiply this to 101, or this equals to negative 1 over 2, 1, and 0, plus 1/4, 101. So you get z equals to negative 1/4, 1, and 1/4. So now we got three orthogonal vectors, this one, and this one, and that one. And once you got orthogonal vectors, then we have to normalize all those vectors to build an orthonormal basis. So basically, well, u1 equals to v1 over the magnitude of v1. That equals to, so we had v1 over here. So we have 101 times 1 over its magnitude, which is square root of 2. And similarly, we set u2 equals to this vector divided by its magnitude. So it's negative 1/4, 1 and 1/4, multiplied to 1 over square root of negative 1 over 4 squared plus 1 plus 1 over 4 squared. Then this equals to 1 over square root of, so we have 1/16 plus 1 plus 1/16 and negative 1 over 4, 1 and 1 over 4, or this equals to, so we have 1, 2 plus 16, that gives you 18 over 16, so it should be 4 over square root of 18 times negative 1/4, 1 and 1/4, or this gives you 1 over square root of 18 multiplied to negative 1, 4, and 1. And lastly, if you bring the vector above, so here, this one, then we get u3 equals to, so we had negative 1 over 2, and 1, and its magnitude is square root of, I guess, 1 plus 1 over 4 plus 1, or this equals to 1 over square root of, I guess, 9 over 4 times negative 1 over 2, and 1, or this equals to 2/3 negative 1 over 2 and 1, or this equals to negative 2/3 and negative 1/3 2/3. Now the last step should be, so we can build P and D using all this information so that we can diagonalize A to be PDP inverse. So A equals to, so we use all these vectors as column vectors. So basically, the first one is 1 over square root of 2, 0, and 1 over square root of 2. And the second one is negative 1 over square root of 18, 4 over square root of 18, and 1 over square root of 18. And the last one is negative 2/3, negative 1/3, and 2/3. And you multiply this to the diagonal matrix with its diagonal entries corresponding eigenvalues. So we have 7, 7, and negative 2, and the rest are zeros. And P inverse is simply the transpose matrix of the given matrix P, which is given by 1 over square root of 2, 0, 1 over square root of 2, negative 1 over square root of 18, 4 over square root of 18, 1 over square root of 18, negative 2/3, negative 1/3, and 2/3. So this gives us an orthogonally diagonalized matrix for the given matrix A. So if A is symmetric matrix, then we can write A into a linear combination of some product of orthonormal vectors with eigenvalues. So we say that as spectral decomposition. So let's say A is a symmetric matrix. Then we can diagonalize A orthogonally. So we have A equals to PDP inverse, where P is given by U1 through UN, and UIs are orthonormal eigenvectors, such that U sub I corresponds to lambda sub I. Then this diagonalization gives you, well, A equals to PDP inverse, but in fact, we have PDP transpose that equals to U1, U2, so 1 until UN, multiplied to lambda 1, lambda 2, and lambda n, and the off-diagonal entries are 0, and we have P transpose, where U1 transpose through UN transpose as row vectors. Then calculating this gives you, so we have lambda 1 U1, lambda 2 U2, and so on, lambda n UN, multiplied to U1 transpose through UN transpose. Or if you calculate this matrix product, then this gives you A is the same as lambda 1 U1 U transpose plus lambda 2 U2 U2 transpose, and so on, plus lambda n UN times UN transpose. Or if you write that as a summation notation, then we get sigma from I is 1 to n lambda I UI times UI transpose. So we can write A as a linear combination, a product of eigenvectors and eigenvalues of the given matrix. So the spectral decomposition of A is a decomposition of A into the linear combination of UN, UN transpose. So here, you want to note that, well, if you calculate ui multiplied to ui transpose, then this is, so ui is a column vector, which is n by 1 matrix. And if you take the transpose of it, that gives you 1 by n. So this gives an n by n matrix. So if you multiply lambda I into that and add them together, then we get n by n matrix A as a result. Whereas the opposite, so ui transpose times ui, gives a scalar. And each matrix, uj times uj transpose, is a projection matrix. And this means, so if you multiply any vector into this matrix, then that gives you the orthogonal projection of x onto the subspace spanned by uj. So you want to compare this with theorem 3, the last theorem, in section 6.3 note. So there was a theorem that states that u transpose times x equals to the projection of x onto the column space of the given matrix. So let us construct a spectral decomposition of a matrix A, where the orthogonal diagonalization is given by this. So we have P, D, P transpose, such that P is an orthogonal matrix. So we have two eigenvalues, 8 and 3. So for lambda equals to 8, we have u1, the eigenvector corresponds to this one. So this equals to 2 over square root of 5, 1 over square root of 5. And for lambda is 3, we have u2 as the second column, which is given by negative 1 over square root of 5 and 2 over square root of 5. And if we calculate lambda 1, u1, and u1 transpose, then this gives you 8 times 2 over square root of 5, 1 over square root of 5, multiplied to 2 over square root of 5, 1 over square root of 5 as the row vector. Then this gives you 8 times, so this times this equals to 4/5. And the other one is 2/5. And the next one is, I guess, 2/5. And the last one is 1/5. And at the same time, lambda 2 u2 times u2 transpose equals to 3 times negative 1 over square root of 5, 2 over square root of 5, multiplied to negative 1 over square root of 5, 2 over square root of 5. And this equals to 3 times 1/5, and I guess negative 2/5, and negative 2/5, and 4/5. And so if you add these two matrices, then this gives you lambda 1 u1, u1 transpose, plus lambda 2 u2, u2 transpose, equals to, so if you distribute 8 into the matrix, then this gives you 32 over 5, 16 over 5, 16 over 5, 8 over 5, plus 3/5, negative 6 over 5, negative 6 over 5, 12 over 5, or this gives you 35 over 5, 10 over 5, and 10 over 5, and 20 over 5, or this certainly equals to 7, 2, 2, and 4, and this is exactly the same as the original matrix A that is given above over here.